When we watched that Falcon 9 go up, it was a big accomplishment. We could righteously claim that we were the first commercial nuclear satellite.
Yeah, and I know in the energy industry, the biggest challenge right now is having the most capacity with the least weight.
That's the promise of this nuclear micropower. Make things very, very small, size of a grain of rice. Not a lot of power, but that it can work for decades and you can have many, many sensors.
Why are your betavoltaic systems unique?
It takes several years to make the semiconductor, to grow it. It's very simple to explain, hard to do.
What is your mission statement and why does it matter?
We want to make nuclear micropower available to everyone. We love the idea that we can take tritium and find thousands of uses for it.
Today, we're going to be talking all about a pretty unique company that's tackling challenges straight out of a sci-fi movie. They want to provide continuous power to deep sea and deep space missions, including to Mars. To reach places that people haven't, this company is betting on a pretty tiny piece of technology with a lot of potential. I'm talking about City Labs, a Miami-based company that develops many long-lasting nuclear power sources that can provide electricity for years straight. These compact power systems work where conventional batteries and solar just won't do. They generate electricity from the decay of tritium. It's a naturally occurring radioactive isotope of hydrogen, and it's nothing like the lithium-ion batteries powering your laptops and phones. Last month, City Labs made headlines for launching the world's first commercial nuclear-powered satellite to space. It hitched a ride on SpaceX's Transporter 17 mission. Think of it as a rideshare for several companies' satellites that are heading to the cosmos at the same time. To discuss Transporter 17 and so much more, I'm Molly Glick. I'm the editor at Energy Central, and I'm joined by Peter Cabauy, City Lab CEO. Peter, you've got a really unique background. I read that you studied quantum information physics at Argonne National Lab, and you worked with Dr. Paul Benioff, who is a quantum computing pioneer. So tell us a bit about your research there.
It was a great time to be able to just try out new ideas. Dr. Roy Clark, the director who ultimately became my official advisor at University of Michigan, was always allowed students to try out new ideas. I had funding from another agency, and I was able to choose my path, what I wanted to study. For a little while there, I looked at the stars, astrophysics. I worked in a lab there. Then I worked in laser cooling. But something about quantum computing and quantum information just fascinated me, especially just the idea that a computation could just evolve off of the laws of quantum mechanics, Schrodinger equation, time evolution of the Schrodinger equation could all be just one computation. And that was fascinating to me. But that's far removed from what I'm doing now. The one connection that I could tell you is that while I was at University of Michigan, I attended a business class in entrepreneurship, and I thought, this is amazing. I get to solve any problem that I want and make a business around it. That's great. And with my physics background, there is a sense of like, oh, I can work on chemistry. I can work on electrical engineering. I can work on just about anything because physics allows you to do that. The reality is a little different. When you start working on things, you realize there are limitations to what you can do. But there was one idea in quantum information and quantum computing that struck me. It was this idea by, in the 1960s and 1970s, Rolf Landau and later Charles Bennett. They looked at what is the fundamental limit, the energy limit for a computation. And because of the idea of these big computers and generating lots of heat. I mean, that sounds familiar to what's going on with AI today. They need to cool off these big AI centers. But what is the fundamental limit? You know, if you just look at it from a purely theoretical physics standpoint, and it's KT natural log 2. So a Boltzmann constant, the temperature times natural log 2 per bit erased. That number is extremely small. It's on, I think it's on the order of like 10 to the negative 21 joules for every bit erased. And I thought, gee, that means a computation can be done for practically no power. That's where the connection of nuclear micropower started coming around. I thought about ants when they're walking around, they're sensing, they're foraging for food, they're computing, they're moving, and they do it for nanowatts to microwatts. And I thought, well, what if there was a nuclear powered ant? They could work forever. So our nuclear micropower, it is in the order of nanowatts to microwatts to, you can scale it up to milliwatts or watts if you put enough of them together. But that it can do it for decades, and you can put sensors that are rated for this low power, put it into concrete buildings, into roads, and just embed it, leave it there, set it, and forget it. That is an amazing thought. And I thought, gee, that would be something that I would like to work on. And that was the inspiration for nuclear micropower. Not a lot of power, but that it can work for decades, and you can have many, many sensors, whether it's on the lunar surface or aiding in the power grid or just monitoring the power grid. That's what's fascinating to me, and what everybody here at City Labs gets excited about every day.
Yeah, I definitely wanna get more into the grid applications, of course, as an editor at Energy Central, that I'm really excited to talk about that. But yeah, overall, I think it's so fascinating that you took something from the quantum realm and found an extremely practical application for it. So can you talk about how you went from studying physics to actually going and co-founding City Labs in 2005? What was your path there?
The path was like I mentioned earlier. There was this class in the business school, and my advisor Roy Clark, or he said he had started his own company as a professor, and he had started his own company at that time as like a physicist starting a company. It's like hush hush, we can't talk about that. That's something sinful that we shouldn't be doing. The physicists should be dedicated to start studying fundamentals and not starting businesses, but I went into that entrepreneurship class and I thought this is amazing to be able to work on real world problems to help people to start things that are new, and the research that comes. What I found is, sure, academic research is interesting, but the research that comes out of a company could be even more fulfilling, and sometimes can go even deeper into the basics of materials and things. And yeah, we've worked with universities over time, but, working to start a company every day is exciting. So the company was founded in 2005. We did a friends and family round, and we've had a lot of regulatory adventures and technical adventures, worked with national labs, universities, uh, but it's just been a fun ride.
Yeah, so I want to dive more into the company itself. Can you talk about, from a high level, what is your mission statement and why does it matter?
We want to make nuclear micropower available to everyone. We love the idea that we can take tritium, a radioisotope of hydrogen, and find thousands of uses for it. George Washington Carver, I often say George Washington Carver found thousands of uses for peanuts. We want to find thousands of uses for tritium. One obvious use is my watch. Tritium, this is not something we made. This is an old idea, but a company in Switzerland makes it. It has tritium in little glass vials, and the betas, the radiation hits the phosphors and it lights up. We find that to be a great use of nuclear micropower. But what else can be done? Can it power a pacemaker? Well, we're doing work right now where we're making a tiny little betavoltaic battery that can go inside a leadless pacemaker. Right now, they're using lithium batteries, and it's the size of a AAA battery. The whole pacemaker is the size of a AAA battery. They put the pacemaker in a catheter. It goes up the femoral artery directly inside the heart into the chambers of the heart. They put this pacemaker, but it's so big. That's a lot of hardware in there. And these companies are saying, "Well, can we make it smaller?" Well, lithium's already tapped out of how small it can go. It can always go smaller, but to the energy capacity or the energy density drops off exponentially as you go less than half a cubic centimeter. Well, with beta voltaics, since it's all solid state, the way that it works is it's like a solar cell. It has tritium on top and a metal hydride, and it's like a solar cell. You can shrink it solid state, and it'll keep the same energy density as you're going smaller and smaller. That's the promise of this nuclear micropower. Make things very, very small, size of a grain of rice. So you can have the whole pacemaker as a grain of rice, and it goes directly into the heart. And that's the research that nuclear micropower is promising for pacemakers. There's also the work that we're doing in terms of just power sources for sensors, like I mentioned, for the downhole oil well sensors. You need to monitor this for decades. Be able to see if the well is leaking, or if we're trying to see the health of the well. We're trying to just do more exploration, and we need uh, some some saltwater analysis. That can't easily be done with lithium or chemical batteries. And putting an electrical conduit to every nook and cranny of the oil well is difficult. So having these tiny power sources, something like a chip package, like I'm holding here in my palm of my hand, that allows us to be able to put it right into the rivets that go into the oil well, and yeah, it can handle the extreme temperatures that chemical batteries can't.
Yeah, and I know in the energy industry, the biggest challenge right now is having the most capacity with the least weight. So it sounds like that's exactly what you're trying to solve as well.
Correct. I mean, the power density on these, it's low. It's the energy capacity. If you integrate over 15, 20 years, just one half life of tritium is 12 years. These will work for decades. But when you integrate over all that time, you realize that the energy density is massive compared to lithium batteries. So we get small little trickles, like little droplets, but over time it fills up a huge tank. And that's what we can do with these tritium micropower sources.
Yeah, that sounds really exciting. And I'm curious, what would you say that is your biggest accomplishment so far with City Labs?
That's a great question. Just because July 7th we launched the first commercial nuclear satellite, that's got to be the biggest one. It wasn't just the making of the betavoltaic; it was the regulatory part. Being able to go through over time, we got a general license for these betavoltaics so they could be distributed to anyone across the United States without the recipient having to have their own radiation license. So normally when we send nuclear material from one entity to another, the other entity has to have a radiation license, a full radiation program. We made these so that anyone could receive these devices. The NRC certified these under a general license. The engineering I went into to make it that safe was a big feat, and that happened, in around 2010. And then we had to make sure that these were not subject to ITAR, so that anyone can work with it. Around 2015, there were a lot of companies saying, we want to put these on satellites. And they want us to build the power source for their mission. Eventually, we found out that it requires a presidential signature to send nuclear material to space. And that happens like every 5 to 10 years on a NASA mission, like Voyager back in the 70s, or more recently, like the Mars Perseverance rovers. They had plutonium. But in 2019, there was a presidential memorandum, NSPM 20, that created a framework so that commercial companies could launch nuclear material to space. And like anything that's new, it took many years for all the companies to figure out how does this work. The FAA was figuring out how this presidential memorandum will work. We worked tirelessly for a few years, going through the whole regulatory process with Sandia National Laboratory. They are well known for launching nuclear materials in space, making sure that this was safe. In September of 2025, last year, we received authorization, a payload review to be able to launch. And like you mentioned earlier, it was just, get a ride share on SpaceX and make this happen. And when we watched that Falcon 9 go up, it was a big accomplishment. We could righteously claim that we were the first commercial nuclear satellite.
Yeah, I'm glad you were able to make it into that ride share. To zoom out a bit, I think that a lot of people have a very fixed idea of nuclear. They think of a very large reactor. Can you talk about what makes beta voltaic systems different from that conception? And also, why are your beta voltaic systems unique?
Yeah, everyone thinks of mushroom cloud, or they think of huge cooling towers and Homer Simpson working on those on nuclear power. But we are not a nuclear reactor. There isn't a splitting of an atom. There isn't fission. So we're just depending on radioactive decay of a radioisotope. In this case, say those works with tritium. When it decays, it emits a beta, or really it's just an electron. The electron has the energy of what used to be our old television screens. We had an electron gun who hit the phosphor screen. We would see the images. We don't have that anymore, but that's the way it used to work. And the betas here can come off and hit some phosphors, and like in my watch dial, light up, and you can see it, or in an exit sign. There are many exit signs that are tritium have tritium gas, then the phosphors light up. But we do something a little different. We're bypassing the light part. The electrons go directly into the solar cell that we've engineered so that it can work well with these electrons coming in. It creates electron hole pairs in the p-n junction, and we get electrical current that way. So the concept is very simple to explain. Solar cell, instead of receiving light, it receives electron radiation from tritium. To actually do it, it takes several years to make the semiconductor, to grow it. We work very carefully with microlink devices to make these semiconductors. 18 patents later, you know, we're doing this type of work. So it's very simple to explain, hard to do. We've dedicated a lot of work towards the R&D, the development, making sure we had the supply chain so we can send that out to anyone regulatorily. That's what makes City Labs.
Yeah, speaking of hard work, what has your experience been like fundraising for City Labs? Did investors come to you? Did you pitch to them? What did that look like?
A lot of times when we have this mission of doing nuclear micropower, they're saying like, wait a second, why do we want micropower? They think nuclear, they want megawatts, not microwatts. And we're like, no, it can really help with pacemakers. It can really help with, surviving the lunar night. There's no other way to do that. And the investors, early on, that took a little bit of imagination and really came down to friends and family. Friends and family saying, okay, Peter, you're a little crazy here, but we're going to trust you. And slowly, little by little, convincing the federal government through the SBIR program and also other programs to say, yeah, we need this. We need this technology because nuclear micropower can do what no other power can do. If we want to put hundreds of thousands or millions of sensors on the lunar surface, if we want to find out where the regions of water may be, it can be done from an orbiter, a satellite. But to put a little spectrometer inside of a permanently shrouded crater where it's minus 200 C, I mean, colder than liquid nitrogen, the only way you're going to do is with a tritium micropower. We're working now to be able to put this on NASA CLPS landers and spread many of these around. So it's not just orbit. The lunar surface really needs this, the micropower. But one other thing that CIDEVS is working on, and we hope to launch this next year, is a tritium heat source, a radioisotope heater unit. This is very, very important as we're going to land. I mean, you can have a lander. I think the Firefly has a Blue Ghost 2. They have 60 kilograms of batteries. It's a lot of mass at $1 million a kilogram to be able to get something onto the moon, just to be able to survive the lunar night. And think, they could have done this with like a third of a kilogram using our tritium heat source. It's not a betavoltaic. All we're doing is Sidious is very good at putting tritium into metal and a metal hydride. We have the systems to be able to do this, and we do that for our betavoltaics. We put tritium not as a gas, as a metal. We put the film on top of the betavoltaic semiconductor. But if we grow that film, we make it into a nice chunk of metal, we will, at that point, have the betas get absorbed in the metal. And when that happens, it creates heat. So your thermal power density is extremely high. And your efficiency is wonderful. As far as converting tritium power to thermal power, it's greater than 90%. Those two applications, those two use cases, tritium radioisotope heater units, RUS, is what the industry calls it, and then the tritium betavoltaics for powering sensors, long-term sensors, will make a difference as we're going back to the moon and establishing permanent infrastructure. We're going to need nuclear power to be able to do that.
So let's get into the story behind your recent launch with SpaceX. City Labs launched what you've called the world's first commercial nuclear powered satellite. What's making it possible for this spacecraft to orbit the Earth right now, and why is it a milestone?
It's a milestone. It's not the world's first nuclear satellite. I mean, that's been done before, but it's the first commercial one. Normally, it's governments that send it, NASA or former Soviet Union or Russia or India. But what we're doing is making the first demonstration that we use this NSPM-20 framework. So it's unlocking the age of nuclear commercial power in space. We're powering Mason Peck's chipset. Mason Peck is a former chief technologist of NASA. He's now a professor at Cornell, and he has a company, Tannhauser Gate, where they make chipsets. These are tiny little, kind of look like this, and they can just drop this out of a Falcon 9, and then it's just in orbit. So instead of having a satellite, this is a chip that's just a satellite, and it's, fits on the palm of your hand. Normally those work with solar cells, but what we did is we designed it so it could work with betavoltaics, specifically microwatt power, and it can communicate directly back to Earth independently of its host satellite. The host satellite bus, it measures temperature, magnetic fields. It has an IMU to be able to detect inertial motion. It's a sensor suite. You can put all sorts of sensors on it. One interesting thing is that as we raise the betavoltaic power, we'll also be able to power a GPS so that we can always know where the satellite is located. So by using the nuclear micropower, we don't have to worry about temperature considerations, which normally you have to really look into with designing a satellite. The thermal analysis has to be perfect. If you're going to apply electrical conduits to a satellite just to power this little chipset that we would slap on at the last minute, that's not needed with betavoltaic power. It's going to work regardless of temperature, and it's going to work continuously. So all satellites can have this little chipset attached, and it'll communicate directly to Earth and tell you about the health of that satellite long after the satellite stopped working. And so it's like a satellite attached to a satellite, thanks to betavoltaic tritium micropower.
So, as you mentioned before, beyond the nuclear component, your satellite has solar panels as well. How do those work in tandem together?
Just like I mentioned, that we can put these little chipsets on bigger satellites, and the nuclear micropower will power the chipset, and it will independently communicate down to Earth and do its own operations independent of the host satellite's bus. For Bohr, it had its own satellite bus, its own ability, its own telemetry, and that is powered by the solar cells on the satellite. We considered just doing it all from the nuclear micropower betavoltaics, but in the end, we wanted to make sure that we could. This was a demonstration. We wanted to understand the health of the betavoltaic units, so we said, let's just make the payload nuclear micropower that it could operate independently of the satellite, because that's the ultimate mission, that we can slap on these little tritium betavoltaic powered chipsets onto any satellite, or eventually put this on the lunar surface. And that's what we're working right now with some of the CLIPS companies, where we will put this on the lunar surface so that it can do temperature readings and do vibration testing and seismic testing, and eventually have beacons and PNT, position, navigation, and timing, to help landers come onto the lunar surface. Because there isn't, at this moment, on the moon, there isn't GPS. We just don't have GPS. So we're going to need lots of sensors and devices across the surface of the moon. And to do that with those extreme temperature swings, going to need nuclear micropower.
And that's going to help crewed missions going to the moon eventually so they can make their way around the surface?
Yes, in many ways, not just in position, navigation, timing. It's going to help in knowing. We have a proposal with NASA right now so that we can have seismic mass sensors that can tell what's underneath the regolith, because if we're going to start building, we need to know what's underneath the regolith before we start building. So seismic sensors are going to be needed, beacons, all sorts of devices.
And are you working at all on what will actually power future missions, maybe even civilizations on the moon and beyond? Are you thinking about the power sources for the people spending all their days there?
Nuclear micropower can only go so far, but nuclear reactors will need nuclear micropower around it. There are places that you need a sensor and maybe hot, and lithium batteries aren't going to work there. So putting these little nuclear micropower devices in and around reactors will be very helpful. They're to some extent radiation hardened. This is something where we can help, but eventually you definitely need nuclear power to be able to survive those long nights and provide a home for our astronauts.
And do you have any other goals for space, for future missions or civilizations there that you think your technology could play a role?
As far as Mars, right now we have plutonium heaters and RTGs, radiothermal electric generators, to help with rovers. So that's plutonium is always going to be great, but we do see the ability to spread many sensors across the Mars surface. We know very little about the Martian weather. I mean, we have a good idea, but to know more is going to be very helpful as we try to go to Mars and to spread hundreds of thousands of sensors around the whole Martian surface. As it could be as a lander is coming, to be able to just drop these out and let them fall where they fall, and they're pretty robust, these devices. So we could put many of these and have it like little weather sensors detecting. And that wasn't an idea that was original with City Labs. It was this was something that came out of NASA Ames, and Jay Bookbinder was the one that was telling us this approach. And we're excited to be able to put lots of sensors that are powered by betavoltaics, trading betavoltaics on the Martian surface, even beyond. There's a possibility to use these for deep space missions. The half-life of tritium is 12 years, but the devices can work for decades. So as long as we account for the length of the mission, we can put enough fuel, tritium fuel, to be able to power devices where solar power is not possible, or it's very shadowed. As we start getting out to Jupiter, there isn't as much solar light that solar panels can get electrical power from.
And as your tech is moving deeper and deeper into space, I know that they don't require any maintenance, which will be really important for these missions. But how is that possible?
You always have to engineer the device, so the electronics will have to be engineered so that it can operate with the beta voltaics on a duty cycle. As far as possible in terms of raw power, thankfully, radioisotopes, they're very consistent. If the half-life is 12 years or 100 years, you're going to get that power no matter what. But you need to have a converter that can last that amount of time. With beta voltaics, given that State Labs has been around for 20 years, the first beta voltaics we made were in 2008. So we're going on 18 years, and they're still working. In fact, we had Lockheed Martin Missiles and Fire Control testing our devices for over 5 years, and they did everything to try to kill these poor little devices. They did extreme temperatures, thermally shocked it, vibration, and they survived. And then they delivered it back to City Labs, and then we sent it to Tom Adams, Naval Surface Warfare Center in Purdue, and he did a lot of testing on it. Went to University of Michigan. They did some more testing, and they put it with some of their micro-powered electronics, and it powered it for several years. And then it came back to City Labs, and after a while we started realizing we shouldn't do any more testing on these. These are valuable just to look at the health of these. So now every so often we'll get a data point to see how the voltage and the current's doing, and it's working like it should.
That's pretty incredible. And you're talking about extreme conditions, maybe not as extreme, but I know the grid here on Earth does have its challenges from all kinds of natural disasters, extreme weather. So let's take a trip back to Earth and dive into your work in the terrestrial energy industry. You've worked with the oil and gas industry, testing your batteries to monitor oil wells. So I'm curious, do you think your tech could have any other applications for the energy industry on Earth? Are you working on any new projects, or do you have any ideas in mind that you'd like to explore?
Every once in a while we get a call from someone in the power industry, and from what I understand, and this is not my area, that there are times in remote places where the electrical grid, or there may not be power, but they want to be able to get some monitoring of the lines or the grid, and having these sensors work continuously with, let's say, like some device like this that can just give you some very basic information about the electrical grid and be able to then communicate it out to a satellite. That's very, very useful. And nuclear micropower is something you can set and forget and just leave it there in a rural area for decades and it'll continue to work. So if something goes wrong with the electrical grid and it's in a remote location, yeah, we can get information, some very basic information. You can put, hundreds, thousands of these, line it around the grid, and it'll just be a permanent infrastructure that will give you information periodically.
Yeah, that sounds really exciting because I know the power industry is really leaning into high tech sensors to plan ahead, get ahead of disasters. So I think that could be really useful. And another question I'm thinking about, so your batteries operate in the nanowatt to microwatt power range, but do you have any interest in scaling up, beyond things like microchips or sensors, powering homes, grid infrastructures? Does that have any interest to City Labs?
Well, the interest is always there. It just becomes like, well, the cost. We can certainly put our devices and bring them up to milliwatts or even watts. You just put more and more of them. But at a certain point, it's the cost is just going to be prohibitive for most applications. So it is possible, but I would say cost prohibitive for the most part. Uh, there are places where tritium is more efficient, like in converting heat, and certainly for, let's say, underwater sensors and devices, uh, we can make heat sources that then use a thermoelectric generator to convert the power, and we can easily see watts, even to kilowatts, depending on the use case and the cost and who wants to pay for that kind of level. But yes, it is possible. We do look into it, but where our heart is nuclear micropower. We think that this is something that is um, there's just so much more that we can do in the nuclear micropower range, and it goes back to that example of an ant. It can walk around, it can sense, it can compute, and it can do it for microwatts.
Yeah, so it sounds like the power is in staying tiny. There's so much you can do on the small scale.
Exactly.
So, we were talking about constraints, but I'm curious, what is your wildest goal for City Labs and what is holding you back from doing that? And could you see eventually overcoming those barriers?
Right now, we're coming off an all-time high with this launch. We were able to do what no other company has done up to this point, which is launch something nuclear into space. We've also looked at the supply chains. We've looked at, let's say, US DOT, be able to travel from City Labs with our power sources all the way to the launch pad. And we've come up with a pathway for everything. So policy-wise, if you would ask me this question 6 months ago, I would have told you, yeah, there's some things there that we need to prove out. Right now, we're feeling pretty confident that we can launch, that we can deliver this to anyone's home if needed. So it's looking pretty good. In terms of supply chain, it's looking great. Tritium, it's naturally occurring in the upper atmosphere, and that's true. There's plenty of tritium in the upper atmosphere, but it's also a byproduct of nuclear reactors, and specifically CANDU reactors. That tritium is there, and we get to repurpose it for our applications. In terms of wild, exciting things, yeah, we'd like to see the lunar surface covered with nuclear micropower. We'd like to see oil wells using nuclear micropower. We'd like to see it in pacemakers. We're working with we spun off a company called Photonic Medicines. We have like a small stake in it, and that company is making a tritium eye implant. It goes directly into the eye for patients with diabetes that are exhibiting diabetic retinopathy, that they're going blind. The first indications from laboratory testing is that this will help. Having that small amount of light that is so imperceptible that you can sleep with this prevents the eye from losing sight through diabetic retinopathy. And I'm not a biologist, even though I'm a physicist and I think I can jump into different areas. But it seems like it's giving some good indications, and we're excited to see where the next steps are going. So in terms of being wildly successful, I see the inception points right now. We're doing all the right things, and if it can just grow, it's going to be exciting.
And what's your next closest milestone that looks like you're going to achieve in the next few months or years?
And next year, we plan to launch that heat source, and that'll be a demonstration that gets us to the high TRL level and regulatory readiness level. And that will be the heat source that we will put on the lunar surface. There's also putting these betavoltaics on lunar landers, and we're talking to the NASA CLIPS companies right now. It'll be great to have the first devices on the moon. Those are the really exciting ones. Terrestrially, like I mentioned, that company, Photonic Medicines, that's exciting to think that it could, it's such a big market, especially as more and more people finding that they have diabetes, to offer a way to prevent vision loss. That's exciting for us. I would also say that there's one thing that we're working on. It's tritium propulsion, and it's a tritium ion engine, and that will allow small satellites to have nearly endless thrust. And that's one of these things that these small satellites, they put them up there, these 1U, 2U, 3U satellites are very small, but they just don't have propulsion. They can't do station keeping. They can't stay over a specific area and do observations. To enable that could be a game changer for the satellite industry.
To wrap things up, when you're looking 5 to 10 years from now, what does success look like for City Labs? And what do you hope that this launch leads to?
Nuclear micropower on the lunar surface, being used, millions and millions of the devices, sensors, beacons, position, navigation, timing, heaters all over the lunar surface, satellites with tritium propulsion, small satellites that can do what large $2 billion satellites can do. You could put like 10, 15 small satellites with this tritium propulsion to do the same thing that those big satellites do for a fraction of the cost. To be able to put tritium power on Mars and into outer space, but also terrestrially, that we are covering oil well sensors, and I would say applications that engineers, your listeners say, we could use microwatt power for that particular use. Well, we just don't know it because SpaceX doesn't have the imagination, but the engineers and the listeners here say we could use that for this application, this use case in industry that'll make people's lives better. That's where we really get excited. That's where SpaceX success really goes to the next level.
Thanks, Peter. So, to our listeners, it sounds like you have some homework. We want you to think big with this tiny technology and see how you can apply it to the grid. Peter, thank you for joining us.
Thank you.